Hi everybody, welcome to the first of two lessons from Module 3, which is on repeated measures designs. So let me start by explaining a little bit about what a repeated measures design is. Repeated measures designs are also called within subjects designs, and this is when you've got multiple observations on the same sample. And we want to compare those observations, okay? So I'll give you some examples here. Is there a difference between people's systolic blood pressure? Systolic, I believe, is the top number on the blood pressure reading. Measures in the left arm versus the right arm. So this would be, you've got a set of one sample of people, and we want to check left arm versus right arm. So we've got two measurements on each person. And I'll point out here that in order to be able to compare them, they have to be the same units. If you've got, it's possible to have repeated measures and them not be comparable. So if you're looking at the relationship between, I don't know, somebody's IQ and their height, you couldn't compare those. You'd have to look at the relationship between those two, which is we're getting to later in the semester. But right now we're looking at, comparing them. So something like somebody's IQ when they're 10 years old and their IQ when they're 30. Looking at, comparing those to see if it has changed over time. So here's our first example with the blood pressure. The second example, do identical twins develop appendicitis at different ages on average? I actually made that up because my mother and her identical twin sister got appendicitis within 2 weeks of each other. And it just made me wonder. But so we actually have, in this example, each set of twins would be one individual. So set of twins A would have twin A and twin B, how old they were when they got appendicitis. So we've got two different people in each pair, but it's still repeated measures because they're paired up. And in this third example, we've got athletes running a race at three different elevations. Maybe one is sea level, one is above sea level, and one is below sea level. And we want to know, does that impact their performance on the race? So these are all within subjects designs where we'd want to know, how does some treatment impact the same individuals or the same sampled individuals. I put a couple of examples here for contrast. These are between subjects, which is what we've been doing. Do Cuban children score higher on an international math test than Argentinian children? Those are two separate samples. And if we wanted to compare them, we just do an independent samples t-test on them. So that would be between subjects. Do men earn more than women? That's a between subjects design because we've got a group of men and a group of women and we want to compare their earnings. It would be possible to pair up the men and the women in some way. Maybe you're looking at siblings, or if there's some other kind of relationship between the men and the women, where, in your data set, the first man and the first woman are paired in some way. That could be a paired design, but just men and women would be between subjects. So there's only two hypothesis tests we're going to be looking at in this module. The first one is a paired t-test, which is what you use if there are just two measures that you want to compare. If there's more than 2, then you have to do something called a repeated measures ANOVA, which is what we're going to talk about next class. So let's get started with the paired t-test. So the paired t-test, as I said, is when you've got differences in data that you've got 2 observations on them, but they're repeated measures. So I've got this example here, which I made up. You've got 6 people, and they measured their temperature in the morning versus in the evening. And we want to just know if people tend to run warmer morning versus the evening, if there's a difference at all. So I'm going to do a little bit of explaining here just to walk you through what a paired t-test is and how it works and what it does. I don't expect you to do all of this every time, so a lot of this is just to give you an idea of what's going on here. So the paired t-test is a one sample t-test in disguise. We actually we compute the differences. So if we were to take these differences, and it doesn't matter whether you do morning minus evening or the other way around, as long as you're consistent. 98.5 minus 98.9 gives us negative 0.4. And we do all of the morning minus evenings like this. Those differences are labeled D, lowercase d. If you notice that, so if another piece of notation, if we were to take the mean of all those differences, we'd call that x bar d. If we were to look at the population mean of all those differences, that's mu d. The standard deviation, the sample standard deviation of all the differences is SD, and then the number of differences, the number of pairs is ND. All of that's with a subscript. So if you notice, say we're talking about a population here. If that population mean is 0, meaning the mean of all of those differences is 0, then these 2 observations are the same. Okay, we've got one of these where they're the same. This person was the same morning and evening. If they're all like this, then mu d is going to be 0. Or if they all average out to be that, mu d is going to be 0. If there's a difference between them, between morning and evening, then mu d is going to be not equal 0. If you subtract it as, in this case we did morning minus evening, if those values on average are positive, so if mu d is greater than 0, that means that morning temperatures are greater than evening temperatures. And then the other way around if mu d is less than 0. We're not actually going to write out these hypotheses every time, but I just wanted to show you that this is what we're testing, essentially. Our null hypothesis is that the difference in the means is 0. And our alternative hypothesis could be that the difference is less than 0, greater than 0, or not equal to 0, depending on whether you want the one-tailed or the two-tailed version of the test. So I went ahead and put this data into SPSS. And to run this one sample, or not the one sample, to run the paired t-test, paired samples t-test, you just go to Analyze, Compare Means, Paired Samples t-test, and then you put your 2 variables, You move your two variables over here to variable 1 and variable 2, and then you just click OK. And we get our output. I pasted our output down here. We'll come back and we'll talk about assumptions and effect size here in a minute. I actually meant to put them below this, but that's all right. So we've got in our output, we've got the means and standard deviations and sample sizes for all of our pairs. They give us the correlations, but we're not going to do anything with that right now. What's going to be important to us is primarily this sig two-tailed. This is the p-value for the two-tailed test. Also important to us, there's our test statistic. And they also give us this mean here is x bar d. And then this standard deviation is s d. All right, so based on looking at this, for our test, if we're running a two-tailed test, our p-value would be 0.491, which means that we would not have sufficient evidence to conclude that there's any difference between the morning and evening temperatures. If we wanted to run a one-tailed test, we'd have to divide that by 2. So divide by 2 for our one-tailed test. All right, and that would be the test that that the morning temperature is lower than the evening temperature. So that would be the one-tailed test. All right, so that's our hypothesis test. Let's talk a little bit about the assumptions. So there's really just one assumption, and that's that the differences follow approximately a normal distribution. Although, as we've seen in other t-tests and ANOVAs, the t-test is robust against mild departures from normality as long as the number of pairs is large. Okay, that's our friend. It says that essentially, as long as we have a large enough sample size, we can do whatever we want, which is not exactly true. But now here we don't have a large sample size. So what we really should do is compute these differences. And I'm going to do this now. So under transform, compute variable, I'm going to compute the differences as morning minus evening. So when we do that, we see our differences, and then we run our regular normality diagnostics on this. Although I don't think it's looking good for that to be normal based on what I'm seeing here. But let's see. So explore. Let's make sure we get our normality plots with tests. The histogram with only 6 observations isn't going to really show us anything, but we'll look at it anyway. And if we click OK, Let's see, we've got a skewness of 1.204, a kurtosis of 2.372. Those are not great. Kolmogorov-Smirnov tells us we've got a p-value of 0.2, which actually isn't bad. So that would tell us that we have not violated the assumption. Our histogram, with just 6 observations, it's hard to tell. And same thing with the normal probability plot. We do have one outlier, but with just 6 observations, it's hard to say anything about that. So I think with all of this information, I guess you'd go by the Kolmogorov-Smirnov test. In reality, 6 is an awfully small sample size. If it's the best you can get, you go with it, but it's way smaller than you'd like to have. Anyway, so what you'd probably do if you were running this and hoping to publish in a journal or something, you'd run this and you'd say, okay, well, the p-value on the Kolmogorov-Smirnov test is 0.2, which is an indication that there is not a substantial departure from normality. However, as I said previously, you all have done normality assumptions, and I think you've paid your dues on normality assumptions. So I wanted to show you how to do that, but I'm not going to make you check for normality every time. Only if it specifically asks for it in the problem. The effect size. If you remember back from the one sample t-test, so from the one sample t, we had Cohen's d, and that was calculated as the sample mean minus the hypothesized value over the standard deviation. That's what this is. It's just that instead of x bar, now this is x bar d. The hypothesized value is 0. And then s is sd. So the mean and the standard deviation are both the mean and the standard deviation of the differences. And then this is 0. So this is the same thing as we saw before. And we've got the same guidelines there, 0.2, 0.5, and 0.8. So for our example here, we've got our standard deviation, our mean, do the absolute value of negative 0.1833, and then we're going to divide that by the standard deviation of the differences, so 0.6047. So that's positive 0.1833 divided by 0.6047. So 0.3031. So now all that's left is to do the write-up. And I said I wasn't going to make you do all of this. Let me just clarify what parts of it was what. This whole thing where I was computing the differences by hand and looking at this and actually setting up the hypotheses, that was just to introduce and explain to you what the one sample t-test is and what it does. I said the one sample t-test, didn't I? The paired t-test is and what it does. Although it really is, yeah. They're basically the same thing. What I do want you to do is check the assumption of normality only if I say 2 in the problem. do the effect size if it's significant. You don't have to do the effect size if it's not significant. And then do the write-up. I put the effect size in here anyway, just so you'd see what it might look like. So it's the same thing as before. You know, a statement saying what the test is doing, stating the descriptive statistics, if there are any assumptions that you're testing, talk about those, and then talk about your results. So our statement explaining what we did, we ran a paired t-test to determine if there's a difference between body temperatures in the morning versus the evening. In the morning, the mean temperature was 98.47, I should put degrees Fahrenheit, and in the evening, the mean was this with the standard deviation of this. And we should put units on that. We went with the two-tailed option here because of the way the problem was phrased. The test did not show a significant difference. And we stated T, the test statistic, and the p-value. And then I went ahead and stated the effect size. So that's it for this lesson, and we can go over some more in class if you want, but otherwise, if you have any questions, as always, please let me know.